In yesterday's video, we gave procedures for adding two vectors together, subtracting two vectors, and then multiplying a vector by a single real number, which is called scaling. Today we're going to talk about a technique for multiplying two vectors together, which is called the vector dot product. Today we're going to learn how to calculate the dot product of two vectors, and then we're going to look at one of its quintessential applications in physics, which is to calculate a physics quantity called work. The dot product is a technique for multiplying two vectors together. And the reason why this operation has its own video and was not part of yesterday's video is that, unlike addition, subtraction, and scaling, multiplying two vectors together is not exactly component-wise. As a matter of fact, the dot product of two vectors is pretty special because the result of that is going to be equal to a real number and not even a vector at all. To give you the formula, suppose that we have two vectors, one of which is called v and one of which is called w. The dot product of these two vectors is denoted by v and then a big old dot and then a w. Now, unlike when we're multiplying real numbers together, where we have a couple of different options in terms of how to represent multiplication, when we're taking the dot product of two vectors, this dot is not optional. You absolutely need to have this dot in between v and w if you intend to communicate the dot product. That's because there are other ways to multiply two vectors together which have other notations. That's the sort of thing that you'll study in Calculus 3 if you take Calculus 3. Now, the formula starts out almost component-wise. You take the product of the two x components, and you take the product of the two y components. x1 times x2, y1 times y2. But instead of using these two numbers as the components of a third vector forming the result, instead, you're going to add these two numbers together. x1 times x2 plus y1 times y2. So as a note, the result of this operation is not a vector. There are no angle brackets in this formula. When you dot two vectors together, you always get a real number. You always get a scalar for the result. To give you several examples, let's calculate the dot product of -1, 3, positive 5, 2. So to do that, I'm going to take the product of the two x's and the product of the two y's, and then I'm going to add those two numbers together. So this will be equal to -5 plus 6, result, the number +1. The dot product of 2, -1, and 3, 4. I'll take the product of the two x's, 3 times 2, and the product of the two y's, -1 times 4. And then I will add those two results together. So that's 6, take away 4, and we get the number, the scalar, 2. And for one final example, we have 1, 3, and 3, -1. I'll take the product of the two x's and the product of the two y's, and then I'll add those results together. So I get +3 plus -3, and the result is the number 0. So, when you're taking the dot product of two vectors, the result is always a number. Now, why do we define the dot product of vectors in this particular way? In mathematics, whenever we create a formula or a definition, it's because that formula represents something that has some use in a real-world application. So taking the dot product of two vectors is something which is useful, and in particular, one of the primary uses of the dot product is to calculate a physics quantity called work. This is already filled in because I'm re-recording the first half, which I lost due to an audio glitch. Now, work in physics has a very specific meaning. Work, quote unquote, is a measurement of how a force affects a moving object. For example, suppose that your moving object is a minecart, which is moving along a track. As the minecart moves, a person puts their hand on the back of the cart and pushes it forward. Now, intuitively, we might expect that because the force from the person's hand is moving in the same direction as the minecart's movement, the minecart will probably speed up as a result of the extra push. Work is what tells you how much the minecart will speed up as a result of the push forward. In the case that the minecart speeds up as a result of this extra external force, this would be a situation where work is positive. Work is a positive number if the force speeds up the moving object, and the size of the work, the size of this number, is what tells you how much the minecart speeds up. Now, suppose conversely that the minecart was moving forward along a track, but a person stepped in front of it and pushed on it to try and slow it down. In this case, because the force and the direction of movement are opposed, the minecart slows down. In this case, work would be considered a negative number, and the size of the negative number is what would tell you exactly how much the minecart would slow down as a result of this opposing force. So what I've written below is a summary of what is called the work-energy theorem from physics. And the real work-energy theorem is a formula that can be used to determine exactly how much the speed of the object changes. Sam, go ahead and throw the work-energy theorem on the screen for a second, just so folks can get a look at the formula. Now, how do we actually mathematically calculate the work done by a force acting on an object like the minecart as it moves? If the force is represented by a vector F with a vector arrow, and the movement of the object is represented by the vector called d, then the work done by the force as it acts on this object moving along this straight line path represented by the vector d, the work done is really simple actually. It's equal just to the dot product of the force with the movement vector, force times displacement. Suppose, for example, that we have an object which is moving along a straight line path which is represented by the vector positive 3, 0. Now, as this minecart is moving, a force is acting on it, represented by the vector 1, negative 1. So the question is, what is the work done by this force on this moving object? Now, the first thing that I'm going to say is that I expect the work done to be positive, because the direction of the force is roughly speaking in the same direction as the object's movement. So it's sort of helping the minecart along the way and pushing it forward, and so I expect the work done to be positive because I expect the minecart to speed up. Now let's go ahead and calculate the work and see if we are right about that. The work done can be found by taking the force vector and dotting it with the vector representing the minecart's movement. So the result of that would be 1 times 3 plus negative 1 times 0. Result 3 plus 0. Result, positive 3. Positive, as we expected. And therefore, by the work energy theorem, the object would speed up. Now let's consider a slightly different example. The minecart's movement is along the same displacement vector. We're still going 3 units to the right. But this time the force vector has a negative x component. So it's pointing down and to the left. Now intuitively, I'm going to expect that the work done will be negative, because overall the force is acting mainly in opposition to the minecart's movement. So I expect that the force is going to slow the minecart down. Okay, now if I actually calculate the exact work done, I can achieve that by taking the force vector and dotting it with the movement vector. So that's equal to -1 times positive 3, plus the number -1 times 0, result the number -3. And since the work is indeed negative, the work energy theorem confirms my intuition that the object will slow down. Now this formula only works for objects which are moving in a straight line path, so that straight line movement can be represented by a vector, which is a straight arrow. But most of the time, objects don't move in straight lines. They moved in curved paths. So it's a natural question to ask, how do we calculate the work done if the object's movement is not in a straight line? And that's something that you will have to wait to see. That is covered in Calculus 3, how to calculate work done if the object is moving along a curve and not along a straight line path. The formula given above only works for straight line movement. That concludes today's material. Today we introduced the formula for the dot product of 2 vectors. The dot product of 2 vectors was equal to a real number. In terms of physics applications, that real number represents the work done by a force on a moving object. And the sign of the work represents whether the force is causing the object to speed up as it moves along or to slow down as it moves along.